Welcome and thank you for joining me, Miss Trott, once again for Math and Science for Young Children. In each of our sessions, we are going to be reviewing math, science, and early childhood concepts. Our goals for this session are to understand concepts of spatial relations, identify spatial thinking and vocabulary used in ramps and ball explorations, and analyze constructivist aspects of ball run constructions. Make sure you download the note sheet to go along with this video and stick around as we learn more about math and science for young children. Our math focus is spatial relationships. Spatial relationships are defined as the relationship between objects and spaces. This is used in your everyday life with driving, placing furniture, and using a map. Giving children an opportunity to practice their spatial relationships could include activities like blocks and other construction materials that involve manipulating and organizing shapes into various positions. Puzzles, which require children to move pieces by turning and flipping. Dancing, movement games, and songs develop a sense of where their bodies are in relation to objects in space. Navigating climbing structures and obstacle courses involve physical coordination while moving through space. And making maps is a way to represent and model space through drawings. Spatial vocabulary is embedded in understanding what spatial relationships are. There are location and position words such as on, off, on top of, over, under, beside, behind. There are movement words like up, down, forwards, backwards, around, and through. There are distance words like near, far, close, shortest, longest. And transformation words like turn, flip, rotate. Spatial relationship vocabulary can get very confusing, and for this reason, lots of visuals, gestures, and kinesthetic supports are important for teaching these concepts to young children, especially English language learners. There are three big ideas when dealing with spatial relationship concepts. Number one, relationships between objects and places can be described with mathematical precision. Children come to know that where something is can be conveyed by talking, drawing, writing, and creating models to represent movement and direction. Number two, our own experiences of space and two-dimensional representation of space reflect a specific point of view. Teachers can help children develop awareness of perspective, the understanding that spatial relationships look different when viewed from different positions. Positions and locations are described in terms of relative to ourselves. The ability to truly decenter and think about how something looks from someone else's point of view takes time to develop and cannot be taught or forced. It will take some time for children to understand that when they are facing a friend, something on his left appears to be on their friend's right. Number three, spatial relationships can be visualized and manipulated mentally. Learning how to hold a spatial representation in the mind's eye can be challenging for young learners. They build proficiency in this skill when teachers provide concrete pictorial examples and experiences with spatial transformations, such as cutting an item in half, flipping it upside down, or rotating to make it fit. So think of a puzzle. A child might take the same puzzle piece and move it all around until it fits, but when it can be visualized and manipulated mentally, they can look at the puzzle piece and the open space and decide which direction they need to turn that puzzle piece to make it fit. STEM is a concept being integrated throughout all educational experiences, but we also need to include it in our early childhood years. STEM stands for science, technology, engineering, and math. And a great deal of emphasis is being placed on that E for engineering. Engineering is everywhere. Engineers are people who use mathematics and science knowledge to design, create, or modify things so that they will be useful. There are many different types of engineering, generally divided into four main branches: mechanical, chemical, civil, and electrical, though there are even more engineering branches. Mechanical engineers design mechanical systems such as engines, tools, machines, and moving parts. Electrical engineers design electrical equipment, systems, and electronic products. Chemical engineers design processes for mixing chemicals. They use science to convert new materials and chemicals into things people can use, such as food and energy products. Civil engineers design and build bridges, buildings, dams, highways, and tunnels. Another kind of engineer is a computer engineer. They design technologies such as computer software and hardware. Science and engineering overlap in many ways, with the exception of their goals. Science proposes questions about the natural world and proposes answers in the form of evidence-based explanations. Engineering identifies problems of human needs and aspirations and proposes solutions in the form of new products and processes. Scientific inquiry is a formulation of questions that can be answered through investigation, where engineering design is a formulation of problems that can be solved through design. Science and engineering practices are parallel and complementary. What does engineering look like in early childhood education? Children are natural engineers who continuously engage in problem-solving activities. They use blocks and other construction toys to build structures, roads, and bridges. They naturally assemble materials and construct things that fit their needs, be it a fort made of blankets, sand castles, or their own inventions. The engineering design process is a series of steps that engineering teams use to guide themselves as they solve problems. The design process is a cycle, meaning that engineers repeat the steps as many times as needed, making improvements along the way. Engineers do not always follow the engineering design process steps in order, one after another. It is very common to design something, test it, find a problem, and then go back to an earlier step to make those modifications or change your design. They learn through trial and error. The design cycle includes ask. First, we need to ask, what are the problems and what are the constraints? And then we move to imagine, brainstorm ideas, choose the best ones. Then we get to the planning part, drawing a diagram, gather the needed materials. Then we move over to create, following the plan and testing it out. The fifth step is improve. Discuss what can be done to make it work better. And then you repeat the necessary steps in order to create the change that you're looking for. The way that young children engage in engineering process is less systematic than we might expect from older children. For young children, the engineering design process does not reveal itself as a step, but rather as a non-sequential component that may be often enacted by children simultaneously, sometimes within a few seconds, and often quickly result in a new question. Much like engineers in the field, the children use, repeat, or skip components of brainstorming, planning, testing, and improving as the project or question dictated. In this session, the exemplar activity is going to be under the engineering design principle about ball runs. Children will use a variety of materials to construct a pathway for a ball or for a marble to travel on and explore ways to direct the ball's movement. They investigate cause and effect relationships as they manipulate the materials in their structures. Using trial and error, children engage in refining their designs, problem solving, and engineering solutions. The underlying science concepts in building ramps is that a ramp is a simple machine that is higher on one end and can be used to move an object from one place to another. Also, the height of a ramp affects the speed of which the ball and the distance it will roll. Use your exemplar activity guide to review the engage, explore, and reflect sections. And after you've completed the activity, you should be able to ask questions about designing the ramps and different types of ramps they can make. To continue learning about ramps, be sure to choose one of the ideas for further exploration to complete. A little background information on ramps is that a ramp is an inclined plane, an even surface that is tilted at an angle with one end higher than the other end. Inclined planes are simple machines that make work of moving things easier. You can use an inclined plane to move an object up or down. Using an inclined plane to lift a heavy object to a higher spot takes less force than lifting it straight up. Things will slide or roll down an inclined plane as gravity pulls them back to the earth from their elevated position at the top of the plane. The steeper the ramp, the more quickly an object will roll or slide down the incline, and the further it will roll after leaving the ramp. The speed of an object moves down a ramp is also affected by friction. Friction is a dragging force that happens when an object rolls or slides against each other. There is less friction for a ball to roll on a smooth plastic track than on a textured foam track. Some ramps that are used in the real world are slides, slanted driveways, wheelchair ramps, delivery truck ramps, slanted roofs, and roller coasters. That wraps us up for this session. Please check all of the other materials that are posted on your course online. If you have any questions, reach out to me or your instructor. We're here to help. Enjoy learning. See you next time.